All right, welcome back. So today it's October 28th, and we're gonna finish chapter 8, and we're gonna get ready for milestone in time 3. Okay, so I think on my notes, on my key, you will see that I have one. I'm sure one carbon for the endo product, but I'm gonna get it right here. I'm gonna fix it up, and then I will fix my key and upload it, update it. Okay. For right now, it's showing like a 6-member ring, but it should be a 7-member ring, and I'll show you why. All right. Sorry about that. So here we go. So what we learned earlier was that this approaches here were intermolecular. So inter means among molecules. So what I'm going to teach you now is intramolecular, intramolecular Diels-Alder, and intra means within itself. That's the meaning of intra. So notice that you're going to learn another term. And by the way, I don't make up these terms. The only terms that I make up are maybe like the double slab or something like that. But when it comes to teaching OCHEM, I like to stick with the terms that are used for OCHEM. Like, all right, what is intramolecular? What is intermolecular? Also, there's a new term that I want to teach you today. Whenever you see something like this, that is long and is all connected, that is known as a tether. All right? So if I refer that to as a tether, you understand that I'm talking about a carbon chain. All right? Okay, so for the Diels-Alders in an intramolecular fashion to work, it requires that the carbon that is the most electron rich be already at 6 o'clock, all right? And it's really, really rich. So for example, if I had this group right here, these Diels-Alders will be kind of difficult to do because this part of the molecule will have to flip. And this carbon somehow will have to be connected to this carbon. You see the difficulty of that. There will be strains in there. So that's why it's important to set it up the right way. So where my electron-rich carbon right there, it's in position to attach to the electron poor. This is electron-rich. And this will be my electronic poor 1. All right. And then we take care of the endo and the exo part, which is easy, right? So right now it says endo. So I have this group already to the left. And it needs to be folded in. All right. Okay. If the Diels-Alder intramolecularly doesn't fulfill these qualities, the reaction will not work. Simply, you just recover starting material. All right. So I'm gonna delete this, and I'm gonna start. Okay. So I'm gonna start here by, and I'm gonna teach you all the steps that I used. So I start with my box here, and I have a double bond here and a double bond here. And I'm going to put the dienophile underneath. And this one will have, I'm going to put this as a CHO group right there. All right. So notice that's the aldehyde group. Right here, I will have an NH methyl. And over here, I have a methyl group. No, not there. I'll have the methyl group right there. All right. Check this out. Hold on, let me write this a little bit to the right so I have more room. All right, like that. All right, so I'm gonna label these carbons in green. So I'm gonna label these carbons 1, 2, 3, 4, and 5. All right. So check this out. Carbon 1 is gonna be sticking out here. You see that? What about carbon 5? To the right or to the left of the double bond on the diene, no file. On the same side as the aldehyde. It's gonna go this way, right? You see that? So I can fill this out with well, I don't need to fill the hydrogens yet. So you have carbons 1 and 5. We have to put 3 more. So what I'll do is I'll go 1, 2, and maybe 1 here, 3, and then I connect like that. So I'm gonna label them now. So it'll be 1, 2, 3, 4, and 5. All right. And then we're connecting this with this, and that with here. And now you can see the approaches now. This is an endo approach. I'm gonna swing electrons here. This double bond will make that single bond. This double bond will migrate here, and this double bond will make that single bond there. So notice that we already have 5 carbons making another ring underneath, plus 2 from that connection right here. This carbon and this carbon. That's gonna make a total 7-member ring. All right, that's gonna be a 7-member ring. And so I'm gonna connect the dots here. Make my box. Let's see. I'm gonna go a little longer so that CHO. Wait, I don't like it. All right, I know what I'm gonna do. Yeah, I'm gonna have a little more leg room there, and I'll have this group inside CHO, the hydrogen on the right side, double bond here, and methyl H. There will be an H that is sticking up and another H that is sticking up, and then carbon 1, then carbon 5 this way with an H on the right side, 4, 3, 2, back to 1. Yep. So in total, I have all these 5 carbons, 1, 2, 3, 4, and 5. Those are right there. All right, I think I'm ready to, and I have a methyl group right here. All right. So the Diels-Alder is a 4+2 cycloaddition, so it will always make a 6-member ring. And at 12 o'clock, we will have this group down. Notice that carbons 1 and 5 will be down. You see that? All right. So over here, so if I label this A, B, C, D, E, and F, that will be A, B, C, D, E, and F. Right? I'll have them here. A, B, C, D, E, and F. There's a double bond between C and B. There's a methyl group on C. On F, my aldehyde group is down. On E, I have a hydrogen that is up, so I'm going to draw it. My hydrogen is up here, and then carbon 5 is down. Likewise, on carbons D, this H is up, so I draw this like if it was a bow tie. Whenever you have two fused rings, you have to show the hydrogens. It is almost a rule in OCHEM. So carbon 1 here attached from D will be like that, will be down. And so I have a 7-member ring. 1, 2, 3, 4, 5, 6, 7. That's that. 1, 2, 3, 4, 5, 6, 7. All right, so I'm going to label that with the green. And this is carbons 1, 2, 3, 4, and 5. Not bad. All right. Do I get a question? Yes, sir. Mm-hmm.
So the dienophile looks cis. So if that fifth carbon, if that was like bowed out and it looks trans, would the 5 be coming towards this?
The 5 would have been up. Mm-hmm. Okay. And you can still do it. Yeah, it's actually a 7-member ring, so it has flexibility. Okay. Yeah.
We can see that in the next one.
Yeah, we'll see that on the next one.
Yeah.
I have a question, Dr. Odin.
Yes, is that Megan?
Yes, it is.
Okay.
I was wondering why we have to show the hydrogens on intermolecular but not on intra and not on inter.
It's a formality, actually. Some people like to write it, some books like to write it, others don't. But if you show me just this one's down, that will be enough for me. Then that tells me that those H's are up by default. You see what I'm saying?
Yes, I do. Thank you.
Yeah, but I always see in books this, I call this like a bow tie. It looks like a bow tie hydrogens. All right, so let's do the exo approach. All right, again, notice that here for the exo, this group has to be on the right. And this carbon happens to be the most electron rich. Also because the methyl group is also adding electrons to the pi bond system. So yeah, that happens to be the richest, electronically richest carbon right there. All right, so like this one was. All right, so let's do the exo approach now. Make my box. And then put my double bond here. This group is going to be forced, this is a ketone, it's going to be forced to be out. I have a double bond here, Oh, methyl, I'm sorry, this is methoxy, methyl on the top. And what's going to happen to this carbon? Is it going to be on the right or on the left on the dienophile? when I flip it. So it looks trans, right?
Yeah, so it's gonna be inside.
Yeah, it had to be inside. It has to go to the left. All right. So let's label those carbons again as 1, 2, and 3. This is 3. 1 will be coming out here, and then 2 will be in between those two. So I just simply make it look like, kind of like, it looks like a, the footrest on a cyclohexane chair. Yeah. So that's how I would do it. And then I'll go 1 and 2. All right, so I'm going to put the dots here for these 2 carbons will connect, and so will these ones. All right, so I'm going to push electrons now. I like to start from the dienophile. But that's just me. Because it's by itself. 1, 2, and then 3. And I'm gonna do now my box here. Had to draw this box as pretty as I can, because Ben likes it pretty, right, Ben? All right, so I have double bond here, methyl, and then carbon 1 will be sticking out like that, and carbon 2 will be down here. Check out with carbon 3, has to be out like that, and then like that. Then there is a hydrogen here that is invisible, not anymore, and there's 1 here. I'm gonna put my hydrogens now, 1 here and 1 here. And then there's a hydrogen inside here. And notice that we have made a 5-member ring, fused ring underneath. So this is 1, 2, and 3. So we start with a 6-member ring. We always have a 6-member ring. Remember, this is a 4+2 cycloaddition. We'll have basically what we'll have is, don't draw this yet, but we'll have a 6 and a 5 fused like that, right? So I'm going to delete this. I'm actually going to delete it. All right, so let's label this again as A, B, C, D, E, and F. A, B, C, D, E, and F. All right, so on A, my methyl group is down. On C, I have a methoxy group. On D, carbon 1 is down. And on E, carbon 3 is down also. And then carbon 2 connects. On F, my ketone group is up. And that's it. All I need to do is maybe the both tie hydrogens. You can draw them. And that's it. There is your fused rings on the Diels order. Yes?
Is the, like you described them as the bow tie hydrogens, is that always going to be the case in these certain kinds of reactions?
Not necessarily. Oh, well, yeah, sometimes. Now, look at this. If carbons, let's see. If carbon 3 was here, then this would have been up. Then you don't need to draw that. Then the H will be down. That H will be down. It depends on what the problem gives you. In these two cases, they turn out to be both of them. Those two groups, carbons 1 and 3, were down, and then the both hydrogens were like both up. But that is not always the case. It depends on what the problem gives you. Make sense? Any other questions? Any questions? All right. So those are the intramolecular examples that I have for you. And let's do now, these are called the bridgehead. Bridgehead examples. All right. I'm going to show you why they're called bridgeheads. All right. So here, notice that you still have to worry about flipping the diene so that your most electron-rich carbon is at 6 p.m. or 6 o'clock. In this case, I have a question here. Would it go to number 1 or number 2 here? Which one's the most electron-rich? Number 1, yes, because you have this electronic push going that way. So 1 wins, and so we have to flip this molecule. So I'm going to flip it. So I will end up with something that looks like this. All right. Then that's going to set my right approach. So I'm going to put it here. I'm going to box it up. In this carbon, I will have my NH2 group. Then, so if I label this correctly as A, B, C, and D, this will be A, B, C, and D. My bridgehead is between A and D. So I'm going to draw it just like I drew this hydrogen up like that. That's the reason why I kept on drawing those hydrogens, just to keep you trained to think this way now. That's how that will go. Up, and the 2 methyl groups will go there. Then over here, you will have your, notice that the dienophile is endo, so this group has to be to the left. So I'm going to put his here, C carbonyl, and with 2 methyl groups. Let me drag this double bond longer so that we can see the connections. And now this carbon will attach here, and this carbon will attach here. Oh, I need 1 more methyl. Ben, where would that methyl go? To the right, to the left? To the right. Very good. Thank you. Excellent. So it's trans, so it stays trans. And then we'll do this double bond will make that bond, that sigma. This will make that, and that will make that. And we'll go and do the 3D connections. Notice that what's happened to the hydrogens on A and D, they're going to be down, right? They're going to be pushed down. We're going to draw them. So I start with my box like this. Always stick to what you know. Wait, let me make this larger. All right, so double bond here, and H2 here. This group goes inside. This is an amido group. This CH3 on the right side. There's an H here, and there's an H here. My bridgehead looks like this. So that means I have a hydrogen here and a hydrogen here. Those hydrogens should be in the downward position. So now we have, I'm gonna fix this up. Gonna make it look pretty. And so that's not pretty. So I'll have that double bond here. And so for the 2D, you have to represent this as down. So in the 2D, you do wedges and dashes. So the group here is down. So this is an amido group. I'm gonna finish it up like that because I started off like that. And the methyl group is up. And I need an NH2 group here. And that's it. Any questions about this? All right. Notice that the 3D connection here for the bridgeheads is almost the same as the 2D. Yes, sir.
So if you wanted to draw like the cyclohexene, like a 6-membered flat, then could you just draw 2 methyls coming up to 1 carbon and then
you could do, yeah, what you're saying, Ben is saying, like, if I might translate this right, you want to say that you want to do this, like you saw the problem of the homework, right? Yeah, you'll go like this. This is another way to do it.
Draw the wedged arrows, so like a carbon in the middle.
Yeah, you do wedge here, represented these are up. Look at that, beautiful. Man, you like it pretty. I see it. I see the trend. All right. And H2.
So do you know how you're going to phrase them, like on the exam and stuff? Do you know if you're going to do it like that or like that for those?
Well, they both tell you the same thing.
They tell you the same thing. Yeah, yeah. To me, I know Ben likes it this way.
Yeah.
I like it this way. Sorry, Ben. But this is correct. This is totally right. Yeah. This is the same thing.
That was a little easier to draw.
It is easy. If it worked for you on the exam, go for it. Because then you can see it and you can translate that from here to here quickly. And then you get your answer. But yeah, that's another way of doing this. Very good question. Very good. I like it. Anybody else? All right.
Doctor.
Yes. Is that you, Bear?
No, it's Aaron.
Oh, Aaron. How are you, man?
Good, how are you?
Good. Thank you.
I just have a question for the bridgehead. Do they not have hydrogens attached to them in any of the right approach 3D connection or product?
Can you repeat the last part?
Do they not have hydrogens attached to them in any of the drawings?
Well, the only ones of interest are these ones. Yes. You know that this is a CH3, so they have hydrogens, but we don't draw those.
Okay.
Because
that's all I'm asking.
yeah, it's mostly bonds here. If you look at it, yeah, we're doing linear structure, so we omit the hydrogens. Notice that this is the reason for the fused rings. Most books want you to represent the stereochemistry of those hydrogens. In this case, it's down. In this case, right here, the hydrogens will be up. All right. Yes, sir.
Do you ever have a case where the bridgehead is down?
Yes, there are cases where the bridgehead is down. Basically, could be down if you flip this 180 vertically. Yeah, the bridgehead will be down. But then your stereochemistry will be also flipped. You see what I'm saying?
So it'd be the same.
It'll be the same, but yeah, if a book tricks you like that, that's too much, I think. I wouldn't go that far to trick my students like that. In other words, you know what I'm saying? It'll be like this. Everything will be opposite. Yeah. Here, this one will be CH3, and this one will be the. All right, and the hydrogens are up now. You see that? And the NH2 will go here. You see that? But that is telling me that the bridgehead is down. Yeah. And this is the same thing as that.
So we always show the dienophile attacking or on the bottom. Can it come from the top?
Yeah, it can come to the top, but then
It's the same.
it's the same thing. And then how do you control a model? Yeah. So with this model predictor, if you stick to it, you will always get it right. Yes. All right, let's do the last one. Notice that you can also do these artists with alkynes. So you will end up with an alkene. Those are easy because then you don't have to worry about stereochemistry. It will be sp2 carbons at the end. Check this out. All right, here. Do we have to flip this group? Yes. To make this is my most electron-rich carbon. So I'm going to flip it. Flip. And so I will start with that. Or I will start off with that. So I'm going to go here. Double. Here's my O-methoxy. My bridgehead here is like that now. How cool is that? Can you visualize it? Then my triple bond is here. And this, and then I don't have to worry about this group. Could be, it's linear. So that's just gonna be rotating within itself, right? So it just stays like that. So I'm gonna do this. And so on this case, same thing, right? And I'm going to attach, these lines here, and this one right here. And I'm ready to do the electronic movement from triple. It's going to turn into a double bond, and this guy is going to become this. It's going to rotate. It's going to make a new double bond there in the middle, and this is going to make the other sigma bond. So I have now this is what it's looking like now. I made two new double bonds. Methoxy group here, H this way, H this way, and this group are sp2. So and so notice that I have these three lines here. That means same thing as. That's what those three lines mean. Like this one, therefore, do you know that?
Yeah.
All right, good. So you learned that in high school. That's good. It stuck with me for ages. Yeah. Exactly. So we're gonna do that. I'm gonna make. Oh, check this out. Check this out. For the bridgehead, what I like to do is this. And I go skip How cool is that? You see that?
Oh, that hurts my head.
That is totally 3D. And then this one come here. Double. No, really. That, and then I'll have, C, carbonyl. This is a carboxylic acid. Another carboxylic acid. I don't need to worry about. The only stereochemistry I need to worry about is the H's here. And they go down. All right. That is it. Any other questions? Yeah, this class goes faster than the earlier one.
How would you picture the final product in another way? Like how
Oh.
would you draw it?
Oh, like
Instead of the-
in your way?
Yeah.
Let's call it the Ben's way. Let me get this together for you. All right. So Ben, this is just for you. You're welcome. I've seen it in books like this. You're gonna get check this awesomeness, because these are sp3 carbons. Check this out. I hope you see this.
Oh, that's
Holy cow, right? Very nice. I know you like it pretty. So I'm gonna have to try to keep it up for you, man. All right.
putting you on your toes with your artistic ability.
I know, right? So you're testing me out. Actually, I took a drawing class when I was in South Alabama, my undergrad. We used to draw people. But I never went to those sessions where they had like a naked model. I always missed them for some reason. I was like, darn it, I was busy. But yeah, we paid like $5 for those, and every time I paid for a model, it was a normal model. So it's fine. It was in the university, so it was allowed. So anyway, so yeah, so we used to like rotate. We had the person in the middle, and we had to rotate and to get different angles. Yeah, so that's how you would draw this bridgehead. Yeah, very nice. Oh, I guess you will have to do one more thing.
Yeah, you got it.
Oh yeah, look at that. Nice.
Didn't you have to do that also on the top product too, to show that those two are not in the plane of the like on the
True. You're right.
you just have too many wedges.
It would be too many wages. What we can do is, if you take this,
Those as like an apple piece.
yeah, throw this as wedges. Yes, that would be better. And then draw these two as normal. That would be better. Man, you're pushing my abilities to the limit today, Ben. All right. So, yeah, so that's how you would do it.
Thank you.
You're welcome. Yes, and I think that's all I have. We're going to have a quick class today. So, any other question? Unless someone there in the online audience has a question, we're going to close it.
If no one has a question, can you go to problem E? I was late and I didn't see it. Like, you don't have to explain
Oh,
it.
yeah,
I just
yeah,
need to
yeah.
draw it in my notes.
Which A?
E.
Oh, E. Okay. Oh, yes. And who is this, by the way?
Caitlin Harden.
Oh, Caitlin. Hi. So, yeah, that's problem E for you. Anything there that you want to see? You just want to take notes?
I just want to take notes.
Got
I'll
it.
see if I have questions.
Yes. Hello. Oh, thank you, guys. I'll see you guys later tonight at 5:30. All right. Have a good day.